Self-healing ceramics for hypersonic systems operate in the most extreme thermal and structural environments we've ever engineered for. Surface temperatures routinely exceed 1,500 degrees Celsius while withstanding vibration, oxidation, and mechanical loads at Mach 5+ speeds. Leading edges and thermal protection systems are at the forefront of this challenge. We rely heavily on ceramics, particularly ultra-high temperature ceramics and silicon carbide composites because of their thermal resilience. But there's a fundamental problem: they're brittle. They don't fail gradually, they fail catastrophically. A single microcrack formed from thermal shock, acoustic vibration, or fatigue can propagate uncontrollably. In current platforms, there's no mitigation strategy for that kind of damage mid-flight. That's where our work comes in. Self-healing ceramics for hypersonic background. High-temperature simulation of thermal protection system cracking. We're developing self-healing ceramic materials engineered to autonomously repair cracks at operating temperatures above 1,500 degrees Celsius. The core concept is this: we embed boron-doped silicon carbide into an oxide matrix. At elevated temperatures, if a crack forms, boron migrates to the damaged region and reacts to form a glassy boron oxide seal. That seal fills the crack, restores structural continuity, and halts further damage propagation. In essence, we're creating a smart material, one that self-repairs in real time during hypersonic flight. No electronics, no actuation, no mission interruption, just chemistry, doing what it's designed to do when and where it's needed most. Mission value, survivability, reuse, and reduced cost per flight. 1. Increased mission survivability. Self-healing materials repair cracks and delamination before they escalate, maintaining integrity under extreme loads. This enhances resilience, enabling longer loiter times and reliable return to base in intelligence, surveillance, and reconnaissance and strike missions. 2. Platform reusability. Many hypersonic components are limited to single use due to extreme stress. Self-healing ceramics extend service life by up to tenfold, enabling reuse across sorties and greatly improving mission efficiency and sustainability. 3. Lower lifecycle cost. More resilient materials cut test failures, reduce replacements, and improve research, development, test, and evaluation predictability, while less damage means less downtime. Technical approach: boron-doped silicon carbide plus reactive matrix. We're using boron-doped silicon carbide for its stability, biocompatibility, and high thermal conductivity. Engineered oxide matrices activate healing at hypersonic temperatures, while nano-silicon carbide, alumina, and hybrid fillers adjust expansion and diffusion for durability. Under thermal stress, boron migrates to crack tips, forming glassy boron oxide seals that close defects and restore load-bearing capacity within minutes. Team composition: government, industry, academia. This joint effort enables rapid transition. TransTech will lead ceramic manufacturing. Penn State and UC Davis will refine design through doping, diffusion, and fatigue studies. AFRL and NASA Ames will perform thermal shock and arc jet testing. And ATI and CoreStech will supply materials and scale production to flight-ready lots. The partnership spans research to full-scale fabrication, ensuring dot alignment and transition readiness. DARPA milestones: what we deliver. 1 6-month demo. Validate self-healing at greater than 1,500 Celsius with less than equal to 70% flexural strength recovery after cracking. Materials will also undergo thermal cycling to simulate flight damage, confirming durability and repeatability of the healing mechanism under hypersonic conditions. 2. Flight-relevant thermal protection system component. Objective: fabricate and arc jet test a prototype thermal protection heat shield tile, then verify survivability across multiple high-T thermal shock cycles without catastrophic failure, that is, no spallation, delamination, or through thickness cracking, confirmed via post-test ND, and retain mechanical properties. temperatures greater than equal to 1500 Celsius, yielding greater than equal to 70% recovery of flexural strength, even after repeated, deliberately induced crack events. Following thermal cycling profiles representative of flight, no ray cracking is observed in previously healed zones, as verified by post-test ND, X-ray, CT, SEM, and digital image correlation. And that's all without redesigning the vehicle architecture, just smarter materials in existing structures. Implications for defense hypersonic systems. Let's step back for a moment. Self-healing ceramics make hypersonic vehicles reusable, lowering risk, cost, and material constraints while extending mission life. They enable safer test flights, longer intelligence, surveillance, and reconnaissance and strike operations under extreme heat, and reduced maintenance demands, fundamentally improving both mission economics and operational flexibility. From lab to flight, enabling the next generation of hypersonic systems. In closing, we believe self-healing ceramics represent a material-level shift in how we build hypersonic platforms, from fragile, single-use systems to rugged, mission-resilient assets. The infrastructure is in place, science is proven, and with the right investment and support, this technology is ready to move from benchtop to flight line. We're not just fixing a weakness in ceramics, we're turning it into a strength. Thank you.